What specific problem does the draw and audio method aim to solve in the context of video Foley, and what challenges does it address specifically related to V2A generation?
The draw and audio method aims to solve the problem of generating synchronized and contextually appropriate audio for videos, specifically addressing the challenges of content consistency, temporal consistency, and loudness consistency in video-to-audio V2A generation. It ensures that the generated sounds align with the semantic content of the video, such as preventing a dog barking sound in a cat-only video, content consistency. Additionally, it tackles the need for the audio to be temporally synchronized with the video events, which is crucial for maintaining the viewer's experience, temporal consistency. Lastly, it addresses loudness consistency by allowing the generated sounds to match appropriate intensity levels, such as increasing the sound of an approaching elephant, loudness consistency. By incorporating the Mask-Attention module and Time-Loudness module, draw and audio enhances the controllability of audio synthesis, effectively overcoming the limitations of previous V2A methods that lacked these capabilities.
How does the proposed draw and audio method work? Please illustrate the entire workflow step by step, detailing key components like the Mask-Attention module and Time-Loudness module.
The proposed draw and audio method operates through a structured workflow that integrates multiple input conditions to generate audio that aligns with video content in terms of content, timing, and loudness. First, it utilizes the Mask-Attention module, MAM, which enhances content consistency by applying binary masks generated from the video to focus on sound-related regions, ensuring that the audio corresponds accurately to the visual elements. Next, the Time-Loudness module, TLM, is introduced, which allows for the incorporation of hand-drawn loudness signals as input, enabling the model to maintain temporal and loudness consistency by controlling the audio intensity dynamically. The model processes the input video and the drawn signals through a latent diffusion model, where the audio is generated based on the combined conditioning sets, including text, visual features, and loudness signals. Finally, during inference, the model synthesizes the audio in multi-stages, allowing Foley designers to flexibly manipulate the generated sounds according to their specific requirements, thus achieving superior performance in audio generation.
Can you provide a specific example that illustrates the inner workings of draw and audio, especially focusing on how video masks and loudness signals influence audio generation?
An example illustrating the inner workings of draw and audio involves the use of video masks and loudness signals to enhance audio generation. When a video clip is processed, the Mask-Attention module, MAM, utilizes sound-related binary masks generated from the video to focus on specific regions of interest, ensuring that the audio produced aligns with the visual content. For instance, if the video features a cat, the MAM will prioritize sounds associated with cats, thereby enhancing content consistency. Additionally, the Time-Loudness module, TLM, allows for the incorporation of hand-drawn loudness signals, which control the intensity of the generated audio. This means that if a loud sound, like a cat meowing, is required, the loudness signal can be drawn to reflect that, ensuring the audio not only matches the visual content, but also varies in intensity according to the scene's dynamics. Together, these components enable draw and audio to produce audio that is temporally synchronized and contextually relevant to the video.
What are the theoretical benefits of using draw and audio over existing V2A generation methods? In what ways does it improve content, temporal, and loudness consistency?
The theoretical benefits of using draw and audio over existing video-to-audio (V2A) generation methods lie in its enhanced controllability and improved consistency across content, temporal alignment, and loudness. Specifically, draw and audio employs the Mask-Attention module, MAM, to focus on regions of interest within the video, ensuring that the generated audio aligns semantically with the visual content, thus addressing content consistency effectively. Additionally, the Time-Loudness module, TLM, allows for the incorporation of hand-drawn loudness signals, which facilitates the generation of audio that maintains both temporal synchronization with the video and appropriate loudness variations, thereby improving temporal and loudness consistency. Unlike previous methods that often lack control over these aspects, Draw-in-Audio enables Foley designers to provide multiple instructions, resulting in a more tailored audio synthesis process. Overall, these innovations lead to superior performance in generating audio that is coherent with the visual elements, enhancing the overall user experience in multimedia applications.
How has Draw-in-Audio been validated? Discuss the datasets used, experimental design, and the evaluation metrics that demonstrate its effectiveness.
Draw-in-Audio has been validated through experiments conducted on two primary datasets, VGG sound caption and audio caps. The VGG sound caption dataset consists of approximately 200K 10-second video clips with caption prompts, while the audio caps dataset contains around 46K 10-second video clips with natural language descriptions. The experimental design involved training and evaluating the models separately on these datasets, as well as on a mixed dataset combining both sources, with 1,000 video clips randomly sampled from the test sets for performance verification. To assess the effectiveness of Draw-in-Audio, various evaluation metrics were employed, including Frechet distance (FD), inception score (AS), Kullback-Leibler divergence (KL), Frechet audio distance (FAD), and clip score of audio and video (CSAV), which collectively measure the quality, diversity, and audiovisual correspondence of the generated audio. The results indicated that Draw-in-Audio significantly outperformed baseline methods, demonstrating superior performance across these metrics.
What notable results were achieved by Draw-in-Audio in terms of performance metrics like FD, IS, and carbon monosulfide AV? Can you explain the significance of these results in the context of existing methods?
Draw-in-Audio achieved significant improvements in performance metrics compared to existing methods, specifically showing better results in Frechet distance (FD), inception score (AS), and clip score of audio and video (CSAV). For instance, it recorded a decrease in FD by 11.3, an increase in IS by 0.38, and an increase in carbon monosulfide AV by 0.66. These results indicate that Draw-in-Audio not only generates audio that is more similar to the target audio, lower FD, but also produces higher quality and more diverse audio samples, higher IS. Furthermore, the improved carbon monosulfide AV score reflects a stronger correspondence between the generated audio and the video content, showcasing the model's effectiveness in aligning audio with visual elements. Overall, these metrics highlight Draw-in-Audio's superior performance in generating temporally and semantically consistent audio compared to baseline methods, underscoring its potential for practical applications in Foley design.
What limitations or drawbacks did you identify with Draw-in-Audio? In what scenarios might it fall short compared to traditional methods or other contemporary approaches?
While Draw-in-Audio presents significant advancements in generating audio with content, temporal, and loudness consistency, it still faces limitations. One notable drawback is its reliance on the quality of input conditions. If the drawn video masks or loudness signals are inaccurate or poorly defined, the generated audio may not align well with the video content. Additionally, the model's performance can be influenced by the quantity and quality of training data, as indicated by the results showing that performance improves with more training data. In scenarios where precise audiovisual correlations are critical, such as in complex scenes with multiple sound sources, Draw-in-Audio may struggle compared to traditional Foley methods that utilize expert human input for nuanced sound design. Furthermore, while contemporary methods like Sonic Vision (LM) leverage vision language models for sound suggestions, Draw-in-Audio's focus on user-drawn inputs may limit its adaptability in dynamic environments where real-time adjustments are necessary.
What future work or improvements do the authors suggest for Draw-in-Audio, and how might these developments impact the field of V2A generation?
The authors suggest that future work on draw and audio could focus on enhancing the model's performance by increasing the amount of training data, as indicated by the results showing improved performance with larger datasets. Additionally, they highlight the potential for further development by increasing the number of trainable parameters, which has shown a direct correlation with performance enhancement. These improvements could lead to more sophisticated audio generation capabilities, allowing for even greater content, temporal and loudness consistency in V2A generation. Furthermore, the integration of additional input conditions and refining the dual classifier-free guidance scales could enhance the model's controllability and user-friendliness, ultimately advancing the field of V2A generation by providing Foley designers with more precise tools for sound synthesis. Overall, these developments could significantly elevate the quality and applicability of generated audio in various media contexts.